Okay, it's my great pleasure and honor to introduce our next plenary speaker, Professor Michael Unser. He's a professor and director at EPFL's Biomedical Imaging Group in Lausanne, Switzerland, and he holds a PhD from the same institution. Now, he's active in the area of biomedical imaging, but he's also internationally recognized for his contributions in sampling theory and wavelets. And he holds a long number of prizes and awards for his research. I'll just mention a few. He's a fellow of the IEEE and of EUROSIP, but also a member of the Swiss Academy of Sciences. He's one of the rare individuals who holds two technical achievement awards from the Signal Processing Society, but also from the Engineering in Medicine and Biology Society as well. And he's one of these rare individuals who's done fundamental contributions to the theory of this area, but at the same time tackled highly challenging problems in the biomedical imaging area. So please join me and welcome Michael to the stage.
So hello everyone. So first of all, it's a real great honor to be here. So that feels like a high point in my career, and I'd like to thank the organizers. So now today's talk is about sparsity and inverse problems, and I will go with the motto: think analog and act digital. So that will be what I want to tell you about. So first, maybe EPFL, so that's my home institution, so maybe you don't know where it is, so I just wanted to show you a photo. So here's Switzerland, and this is Lake Geneva, so a nice area, so if you want to come visit. And so this is like the EPFL. And actually we even have the president of EPFL sitting in this room. So, okay. And so here's what I'd like to cover today. So I'll talk about inverse problems in imaging, give you a short history, and then, as the title goes, think analog. So I'll make a connection with splines, and then I'll make a connection with statistical signal processing, but still in the continuous domain. So that's the think analog and statistical part here. And then we'll go to act digital, and my area being biomedical imaging, so I'll show you how those models and sparsity concept can be applied to biomedical imaging. Okay, so let's start with setting the stage about inverse problems in bioimaging. And so here I take, for example, the case of fluorescence microscopy, where you have a concentration, 3D concentration of fluorophores in the specimen. And so we're looking through a microscope. And so physically, the microscope is some kind of integral operator, and then we're having our measurement on the CCD detector, and there you're adding noise. And so at the end, here you get this blurred image here, but it's in 3D, and you have this linear model here where you have the H matrix represents the physics, so it's a convolution in 3D, and you have this measurement noise N here, and the task is to recover S. And so this is a very, traditional problem, inverse problem. So now first, if you're lucky enough, when your problem is well posed, and mostly it is, like in traditional imaging, essentially here, so you have this kind of mathematical bound, but in this case it's relatively easy, because what you do, you have this matrix H, and if you're lucky it's square and well conditioned, so you just invert your matrix and you're done. And actually there's even the poor man's version of that, and also historically when people invent new modalities, this is the first algorithm they come up with, which is the back projection algorithm. So instead of taking the inverse here, what you take is the projection, the transpose of this H operator. And I mean, this looks pretty simple, but it's, for example, what's used in MRI, because the MRI machine is constructed such that you measure the Fourier transform, and then if you do the H transpose, that's the inverse Fourier transform, and you're able to reconstruct your image. And so that would be the end of the story, but my talk would be very short. Of course, this doesn't really work. I mean, it works with MRI, but because I didn't tell you anything about the noise, so there's the effect of inverting the matrix on N. And then usually the matrix is not square, and it's not well conditioned. And in fact, all interesting inverse problems are ill-posed. So what do we do? So again, here's a nice theory. So it's 20th century theory, goes back to Tikhonov. And here the idea is sort of to introduce some additional constraints. And for example, you define an energy. So L could be the gradient. So you say that you want the L2 energy of the gradient, and then you say, okay, my image after reconstruction, I want, let's say, to bound this energy, and then I want to reconstruct here to have a consistent reconstruction by subject to this constraint. Using Lagrange multiplier, you write it like that. So it's a quadratic minimization, completely classical. You solve your problem in closed form, at least formally, you get this solution here. And the main point here is a linear algorithm. And now what you recognize here is still your H transpose. So that's, let's say, the poor man's version of the reconstruction algorithm. But there's this guy here. And this is what's called the filtered back projection algorithm. So for example, if you take a CT scan, this is the type of algorithm that is implemented. So you do your back projection, but you also have that which is the filtering part. Then how does that connect to statistical signal processing, still like the 20th century view? So here we can make a model. First we assume the noise is Gaussian, and then we go a little further, we make a model of the signal. We assume the signal is multivariate Gaussian. And so here's Wiener. And then you write down your minimum mean square estimator of S given Y. And actually in the Gaussian, under Gaussian hypothesis here, it can be written like that as a maximum a posteriori estimator. Now what's important here is the the CS, which is the covariance matrix of your signal. And so you have, this optimization problem. Now how does it relate to Tikhonov? In fact, if you look at the two formulations, you see they're almost the same. Here you have the data term is this L2 norm, consistency measure, and now instead of the regularization here you would have like the Gaussian prior likelihood, and actually if you interpret here, it's quite interesting because you see that the optimal operator to put here is actually the square root inverse of the covariance, and it is the transformation that will decouple your signal. and so this is the whitening filter. So okay, that was 20th century. Of course, it's not exactly the way it's going anymore because there has been sparsity revolution. And in the sparsity world or compressed sensing world, we still write it in the same way, except we introduce another prior here or regularization. And, just to make it very short, what happened, they went from 2 to 1, replacing L2 norms by L1 norms. And so the most famous case is, for example, still using the gradient and putting L1 norms, so that's total variation. This also works with wavelets. So for example, here's a wavelet transform of the MRI, so it's very sparse, few large coefficients. So imposing a L1 norm on the wavelet coefficient does more or less the same job. And all this is also like supported by the very nice theory of compressed sensing. So what is the current status now in imaging? Well, first of all, this L1 business really works. And there's overwhelming evidence that almost in every modality it gives you better quality. And so that's the reason why people have been reworking every possible algorithms using sparsity. Now the other thing is, okay, there's a cost to pay. It's more complicated. It's not just a linear algorithm, but there are very nice solutions like FISTA, ADMM. I think Professor Boyd, is one of the important contributors there, and for example the ADMM algorithm. And the paradigm is supported by the theory of compressed sensing. But now, what are the outstanding research issues, the way I see them? Can we go beyond L1 and TV? And I believe yes, by making the connection with statistical modeling and learning, and try to develop that. And now the other thing is go beyond matrix algebra. And, my talk is think analog, so I want to promote the continuous domain modelization, formulation. And what about guarantees of optimality? Now, okay, I'm not the first one to talk about continuous domain, let's say sparsity or compressed sensing. There's some work, not so much work, so there's very nice work by Adcock and Hansen on infinite dimensional compressed sensing. There's also nice work on X sampling by Yonina, Eldar. And on the spline side, it's an older story. Actually, it goes back to 75 L1 splines, and more on this in a minute. And then there's statistical modeling, and this is like work that has been done in my group over the last 7 years on sparse stochastic processes, and that's what I want to tell you about also. But before that, let's go back to my old love, splines. By the way, to Milos, who were talking yesterday, this is a spline, okay? But anyway. Let's move on. Splines are analog, so they are continuously defined functions and they're intrinsically sparse. And so what you need is an operator. So this is a differential operator. Take, for example, the derivative. Here's the Dirac impulse. And so here first, let's define our spline. And so it's a function on RD, so it's multidimensional if you want. And this will be a non-uniform L spline with some knots xk if now this strange thing happens. You hit your function with your operator, and after that what you are left is just a stream of Diracs. And so here's the illustration. For example, here's a piecewise constant signal. If you differentiate, now your operator here is the derivative, you're just left with Diracs at the location of discontinuity, and actually the height of the Diracs tells you the height of the jump. And here is a very nice connection also with, like Martin Vetterli, very well known in this audience, in this community. And this is finite rate of innovation, signal processing, and you could think of this thing here, like the stream of Dirac, I call it the splines innovation. And it has like those variables are the knots, so the location of the jumps and the height of the jumps. And by the way, he's our new president, okay, of EPFL. Okay, so now about the spline synthesis, an example. So let's take the derivative. Now what's important with the derivative, the null space of the derivative is the constant. And so here's my innovation. So let's say I'm given the innovation, I want to synthesize the spline. So what do I do? First, I look for the inverse of the derivative, and now apply to Dirac, and this is called the Green's function. And in this case, it's the impulse response of the integrator, and that's a step. And then what I do, I will just integrate this innovation, and which means just replacing all the Diracs by steps. And so that's what I get. And okay, I have still a little problem, maybe like a boundary condition, so I have to add a term that is in the null space, so which is this constant. But essentially what you see here, your spline is a sum of steps, and the steps actually located at the discontinuities. Now, can we generalize? Yes, we can really generalize a lot. So we can take an arbitrary differential operator, again, an operator that would have a Green's function, so that would be the L-1 applied to Dirac. The operator would have a finite dimensional null space, for example, of polynomials, and then here again, the spline innovation. And we want to integrate that. So how do we do it? I tell you the recipe is easy. Every time you have a Dirac, you replace by the Green's function. and so here, if the operator is linear shift invariant, the Green's function just gets shifted, and you have this equation. Now, it looks pretty simple, but the devil is in the details, so you have to put some boundary condition, and that's, where I spend like quite a few years working out the details. But I mean, all this is under control. So now our new optimality result is about universality of splines, and this to me was really amazing. So now you can take some spline admissible operator, and now what we will define is some kind of generalization of this L1 norm. And it's a sort of generalized total variation, and it is defined by duality. Like here, it's like the dual norm here would be L infinite on the class of functions that are smooth and decaying at infinite. And so then you have your general total variation, and now, okay, for those who don't know so much this functional analysis, now in the particular case where LF is in L1, then actually this generalized total variation is exactly the L1 norm of LF. And L can be anything you want, derivative, second derivative, your favorite operator. Now what you do, now suppose now you have an unknown function f, and now suppose you put it in an MRI or whatever, and you get some measurements. And now the only assumption here I'm doing is I get linear measurements. So that would be inner product between my function and some analysis function, and I get a finite number of measurements. This is what happens in imaging. And now here's the amazing theorem. Now the generic linear inverse problem, so it's like in my introduction, it's just here instead of lambda, the L2 norm or the L1 norm, I put this generalized TV, now which is defined here. Then this problem always admits global solution of that form. So you may recognize from my previous slide, so what is this? It's a spline. It's a spline that goes with the operator L, which has some unknown knots, unknown coefficients, and some components in the null space. So to me, this is completely amazing because this result holds for any linear operators. So any measurement, so any linear inverse problem, including compressed sensing and whatever, if you formulate it in this way in the continuous domain with finite number of measurement, the solution is guaranteed to be a spline. Okay, it's an existence theorem. It doesn't tell you how to compute it. There you can run your algorithms, but at least it explains to you what it is. Okay, so that was my first part. So let's become statistical. And so that's an introduction to sparse stochastic processes. And actually, it's sort of the statistical counterpart of my story so far. Let's just take again this innovation, but let's make it random. So now we have Diracs, we have coefficients. So here, for example, is a non-uniform random spline. So the location of the jumps are random, like a Poisson distribution over the real line. Those guys are IID with any distribution you wish. And so this will generate something like that. Actually, this is known as a compound Poisson process. And then you can play the same game, like regenerate by applying the integrator. And now if we want just to formalize a little, here what we have, actually we have a stochastic differential equation. So ds, derivative of my signal equal W, and W now is this innovation. And to solve it, we have to put some boundary condition, for example, S of 0 equals 0. And so here are my impulses, I solve it, like before, I replace the Diracs by step functions, and here's my solution. Okay, so that looks pretty cool. Can we generalize? Actually, at that point, what we recognize is if you take those random Diracs, if you do a spectral analysis, you find actually it's a white noise. Say, wow, okay, can't we be more general? Actually, this innovation, this random innovation, if you look at the autocorrelation, you have a Dirac. So let's just be more general. Let's just pump in every possible white noise we can find. For example, Gaussian, white noise, impulsive white noise, and actually there are other white noises not so well known. For example, there's a Cauchy white noise, and I'll tell you more about the white noises. So, for example, if you take the Gaussian white noise, you integrate, what you get is Brownian motion. So we are back to Wiener. If you take the impulse white noise here and integrate, we get the compound Poisson, so this is, or alpha stable Levy flight. So it's very classical stochastic processes, not so well known by signal processing people, but those are Levy process. But now we can be more general. Now let's, instead of putting the derivative, let's put just any operator. Like here, so we have like our innovation, our way of solving the differential equation, which is applying L-1, you get your stochastic process, and here I call this a sparse stochastic process. And I mean, it's not usually the way a statistician do it, but in fact, we are lucky because the Russians developed the theory in the 70s. It's a very nice theory, Gelfand theory of generalized stochastic process. And actually, those guys are really generalized function. That's the reason why statisticians don't like this white noise. And if you have a generalized function, you cannot look at it pointwise. You can only look at the inner product with test function, like here. And actually, this whole theory of Gelfand and generalized stochastic process is finding the statistical description of the inner product of my strange object with test function, but for any test function. And so that gives you the description of the process. And then, okay, now you solve your stochastic differential equation. You are here, you have your process. But now the good news, the hard work is in defining the white noise, and all the rest is almost trivial, and let me show you so that you appreciate. So here what we do also, we take inner products with test function or wavelets or what you like. Now, with this formalism here, S is L-1 W, W being the innovation. Now we just use a nice trick, is the trick of duality. Here you have an operator, you move it on the other side, and this is like taking the transpose of a matrix. And now you just call this, again, a test function, and you're back here. So actually, if you know what's happening here, you also know what's happening here. You know it comes for free. And actually, at that point here, you can use wavelets or you know, like discrete versions of the operator. You will decouple, and this will do all the regularization. And actually, the main feature here is that those processes on this side, we can show that if we apply white noises that are not Gaussian, they will always be sparse. And so that will be my story. Now, okay, the problem here is really defining this white noise, or that we call innovation. And there's one thing to remember is those guys are infinite divisible. You may not know what it is, but I'll explain to you. But now the difficulty is really like this W is a tempered distribution. And so now actually what we came up is with an axiomatic definition that's relatively simple. So you can almost forget about the math and just by my three axioms. So the first thing is, yeah, we can observe the innovation with the test function. So we do this inner product here, we get a number, and this number is a conventional random variable, so nothing mysterious. Now, if we shift the test function, we get another random variable, so we would like it to be equally distributed, irrespective of the shift. And so this sort of supposes that our innovation is stationary. And the last thing has to do with independence. So it's sort of hard to say what's independence of Dirac's or whatever. So here what we say, if we have two test functions and they don't overlap, so we're looking at the innovation, now the two random variable here should be independent. And actually, with those three axioms, what we can show that, in fact, if we do an inner product of innovation with any test function, we get a random variable that's infinite divisible. So what is infinite divisible? So in some sense, it means we can chop our random variable in small pieces. So this x, which is a random variable, we can express it as a sum of random variables that are identically distributed. And now this we should be able to do it for any n. So we can chop it in as many small pieces as we want, and those pieces should be identically distributed. So it's a little hard to, figure out, exactly what it means, but if you look at the white noise model, is actually pretty straightforward. So let's suppose we can do the inner product between our innovation and rect. Now, here I'm drawing the white noise. Actually, only an engineer like me can draw the white noise because, this is too nasty to be drawn, but I can draw it. So here it is. And now you do an inner product with a rectangle. Now let's just chop our rectangle in small rectangles. Now you agree those small rectangles are non-overlapping, they're just shifted version of each other. So we're in this case here. And so therefore those n random variable will be identically distributed. And of course, I can divide my rectangle in as many pieces as I want. And so in that sense, this is the proof that actually those guys are always infinitely divisible. I made it with a rectangle. And usually, like, infinite divisible laws are characterized by something that's called the Levy exponent. It's just the log of the characteristic function. Now, if we, instead of a rect, put another function, okay, so here's a little drawing, but the end of the story is that this new variable is also infinitely divisible, and it also has a Levy exponent that's related to this canonical Levy exponent. And there's a funny formula because we are kind of integrating this function f, which depends on omega, and here we have put the function phi, and we're integrating over the domain of phi. I mean, the main point here is we can just get the distribution, okay? That's what counts for us. And so now, out of that comes the main property that every probability distribution we want to take of those random process, they will always be infinitely divisible. And how do you do it is the trick, you always go back to the innovation, like Martin has been saying for long. So you apply your operator L, so you get W here, which is the innovation, and then you know the statistics of this kind of random variable. But now let's suppose you don't have W, you have S, and let's say you are doing a wavelet analysis with phi. Now S, you say it's L minus 1 W, you move the L minus 1 on the other side with the adjoint, and you call this a new test function. Actually, you call it phi. And you just use your theory on the white noise, and actually you have the explicit form of the distribution of this random variable. Anyway, the main point is just to say we can take this sparse stochastic process in any domain. We have the distribution. Here's only like a marginal distribution, but we can also crank out all the joint probability distributions. And here are some examples. So for example, Gaussian, so this is the PDF. Now Laplace. Laplace is important for L1 people because if you do a map, it will map into L1. But compound Poisson, so compound Poisson goes with those random Diracs. So you have a mass distribution here, Dirac at the origin, so it means lots of zeros and relatively heavy-tailed. And for example, Cauchy or the family of alpha stable, they're very, very heavy-tailed distribution, but they're also part of the story. And here you just have the Levy exponent. Anyway, so then you can, sort of excite your differential equation with this innovation. And for example, here we can choose an operator like dx dy. So what is the green function of this operator? It's actually a quarter plane step, like here. And so here is like the solution of this differential equation driven by Dirac's, and it gives you this guy here. So we call it a Mondrian process. Actually, I have a screensaver. It looks pretty good usually. I can run it if I get some time. Now, this signal is the signal that will compress really well in a wavelet basis, okay, obviously. It's very sparse, it's obvious. But now you can take other operators like, for example, Laplace. the Laplace. In fact, we can take fractional Laplace. So what is fractional Laplace? So Laplace in the Fourier domain is omega multiplied by omega square. And fractional Laplace in the Fourier domain would be multiplied by omega to some power, not necessarily integer. And so then we can write actually a stochastic differential equation. Now, if we drive our stochastic equation with Gaussian white noise, what do we get? Actually, we get fractals. Fractals used to be very popular maybe 30, 40 years ago. You may know of Mandelbrot and fractals everywhere. So here are your fractals. In fact, those guys are fractional Brownian motion. And the Hurst exponent here is given by the power of the Laplacian. And so those guys look like clouds, or, you know, Swiss mountains, if you look at them you know, as a function. Now, those guys are Gaussian, but now we can also excite the same equation, for example, with the Diracs, and here's what it looks. So that would be the sparse version of Mandelbrot. So, okay. Now, for relatively small Hurst exponent, it looks a little like pointy. But as we increase like the Hurst exponent, it starts looking pretty much like the Gaussian guys. But the big difference is those guys are sparse, those guys are not. So those will compress wonderfully in a wavelet basis. Those, they don't compress so well. Okay, so you would say, what's the relevance of all that to signal processing? I say, look at the extremes. So, powers of 10, you know, you go, you know, like astronomy, you look in the sky, what you see, little stars. Oh, yeah, it looks pretty much like here. Then you go in your microscope, you look at your cell, so this is like chromatin. And you could say, okay, at least there's some images. They don't look like Leonardo's, but they seem to conform with the model. Okay, I mean, you could say, like, is this very relevant or not? I mean, here's my main point now. What's important here, we have a model that will explain sparsity. Now, in the 20th century, people have used Gaussian. Have you ever seen Gaussian signals? There are almost none, except maybe the clouds. Yet there are many algorithms that are based on the Gaussian hypothesis that work really well. And so you can see the Gaussian framework more as a way to crank out algorithms. Now what I'm claiming here, here's the sparse counterpart. Actually, it's also compatible with Gaussian. We are not losing it. It's part of the story. Now, if you take those models and you crank through you apply the paradigm, you will find the L1 algorithms, or the sparsity algorithm. So I'm not claiming true images look like that, but I'm just claiming here we have now a stochastic model. If we apply our tools of statistical signal processing, we will now derive the sparsity type algorithms, but using a statistical perspective. So I think it gives us a pretty good understanding, at least how the algorithm works and the type of signal for which it should be optimal. So let me now tell you about high-level properties of those sparse stochastic signals. So I just said they are infinitely divisible, or the laws. They allow for explicit calculation. So as far as I know, those are the only processes for which you can really derive statistics of wavelet coefficients, DCT, anything you want. It's a unifying framework. It includes everything classical, every family, stationary processes, self-similar processes, ARMA, fractional Brownian motion, and all the non-Gaussian generalization. Now, this is more remarkable. Actually, the sparsifying transform, for example, the independent component, we have evidence, for example, like the Levy process I just showed you in my second or third slide. Actually, the Haar wavelets are independent component for those guys, which is really amazing. And now, if you switch to the Gaussian regime, its DCT becomes optimal. And if you go to the non-Gaussian regime, wavelet become optimal. So it tells you at least it fits the paradigm. And now n-term approximation, because I've been calling those things sparse for at least 7 years, and everyone asks me, you know, why are they sparse? Hey, we finally have theorems now on n-term approximation. We have been able to show that they're included in Bezov spaces, and therefore they are sparse like, you know, in the good old wavelet days. And all this is described in the book here. Okay, so that was my theory part. Let's become practical, act digital. Let's do reconstruction of biomedical images. Now, the first thing here in my talk, I'm continuous. So we need to discretize our algorithm. So how are we going to do? Actually, we do like finite elements. We will choose basis functions. And so we represent our signal as a linear combination of basis functions. So that could be like sinc basis. I prefer splines, so B splines here. And those S here could just be like the samples of your function. Now, what we do, and this is the new aspect here, actually we have our innovation model is in the continuous domain. Now, what we are doing, we are projecting this innovation model on the basis functions. And we can do, because we have a scheme that gives us all the joint distribution of any linear transformation, so we can do that rigorously. And actually, we get a matrix transposition of this continuous domain model is U equal LS. So now S are the coefficient in the basis. L is the discrete version of the operator. And U is what I call now the discrete innovation. And now we know that those guys are infinitely divisible because, I mean, that's the way it is. And now we also need to discretize the physical model. And so here, for example, if I have a microscope, I know this is a convolution with the point spread function. And so I know that my, you know, mth pixel is like, you know, the inner product between the function that I'm looking at through, you know, this shifted impulse response. And so this, I can discretize it like that to write it like in my first slide, like HS plus N. And now this H is a system matrix. It's actually the interaction between the physics here, the nu, and the basis function that I've chosen. And so those are integrals here, but that give me the entries of my matrix. And then I do probability. Now I can use Bayes' law. So what, if in the inverse problem or statistical signal processing, we're interested in the posterior distribution. So Y is the measurement, and S. Now S will be the coefficient of the basis functions. And now using Bayes' law, I know it is like the P of Y given S. So that's actually just the probability of the noise multiplied by the probability of the signal divided by probability of Y, but this can be taken as a constant. And then the other ingredient is this innovation equation. Like I have this discrete innovation U, that's LS. And now that's a linear relation, so that means that the prior probability of the signal is actually proportional to the probability of U. But U, we just said, is independent, so it's the product of the probabilities of U. And then you just do as usual. For example, in the additive white Gaussian noise scenario, you take, you write this posterior likelihood function. So this is the probability of the noise multiplied by the probability of the signal. You take the log and maximize, and you get this. And this will look very familiar because this is just your usual data term, and this is the regularization. And now, okay, what is this phi here? The phi is the minus log of the probability of this innovation, and we know this innovation must be infinitely divisible. So here are a few cases. So if this guy is Gaussian, I find a 2 here if I take the log. And actually, this gives me the L2 norm of LS squared, and this is Tikhonov, okay? If I take Laplace, I get L1. But there are many others, and so this is like a more heavy-tailed distribution. It's more like a log. So here, like those potential functions, so this guy here is non-convex, and this actually goes more with L0. And actually, it behaves like those iteration with p going to 0. So now how do you solve your problem? Now, there's a good trick that everyone knows, divide and conquer, or write easy problems that you know how to solve. So the easy problem, like we could just look at the denoising problem if we just had one pixel. One noisy pixel, we know the U comes from an infinite divisible distribution, so we have to solve this problem, which is a scalar problem, and that's actually called the proximal operator. And it is just because it's a scalar problem, actually the solution here is just a function that given y, our measurement, it will output a u, which is the optimal estimator. And here are some potential functions. So you know that if it's Gaussian, actually this solution of the proximal operator is just a straight line. In fact, this is the Wiener filter, just a linear estimator. If you have L1 here, absolute value is a soft threshold that everyone is using in sparsity. And otherwise, it is another function, but that looks a little like a threshold. It's just not exactly a soft threshold. It's just a shrinkage function. And this goes actually, for example, this case here, the log would go with this LP relaxation. Okay, so now how do we compute our maximum a posteriori estimator? Of course, I insisted this innovation is important, so I put it in red and define it as my auxiliary variable. I rewrite the cost function like that. Just now having the innovation, but introducing the constraint u equal ls. And then, actually I apply the good methods of, convex analysis or iterative methods. Augmented Lagrangian, so for example, here I will introduce a term that makes u get closer to ls, because that's my constraint here. And I also add Lagrange multiplier, so that's the augmented Lagrangian method. So now I kind of create the augmented Lagrangian, now with two auxiliary variables. Now the innovation and the Lagrange multiplier. So the Lagrange multipliers here are just enforcing the constraint ls equal u. And then I will use ADMM. Why am I using ADMM? Because I'm lazy. I'll tell you why. No, it works remarkably well. And so here's my cost function. And now I will sequentially optimize through S, U, and alpha. And let's look at this here. So for example, first I assume the U, the innovation is known, and the Lagrange multiplier are known, and I minimize this cost function here. Then I update the Lagrange multiplier, so that's completely standard. And then now I assume S and alpha are known, and I estimate the innovation. Now the good news is the first problem, okay, if U and alpha are known, what is my solution? Hey, it's a linear solution. Remember my first slide, the second slide, is exactly Tikhonov. Except I'm not like inputting only y, I'm adding this variable that varies during iteration. But that's the reason I'm lazy. I can reuse the algorithm of the 20th century that are in MRI, CT. I mean, they have been optimized. They're very good algorithms. And I can just reuse them by just like tricking them a little by entering some different stuff and solve this first step. So second step, it's nothing to do, just a linear update. And the third step you already know is this denoising step. And actually it's completely decoupled, so it's a pointwise thresholding. So in some sense, this is the easiest algorithm you can come up with. Okay, linear algorithm thresholding, linear algorithm thresholding. And now, okay, what's the story here? Of course, now the thresholding, you should tune to your statistical model, and then it's pretty universal. So let me show you some examples. Fluorescence microscopy. So actually in fluorescence microscopy, the model is a convolution. But it's not a 2D convolution, or as you may be more familiar with, it's really a 3D convolution. And so, for example, here's a point spread function of a microscope. So the thing is, there's a focal plane where it's very focused, and here you have like the airy disk, but otherwise you have like, the light gets blurred like here. Anyway, the physics are pretty well understood, so that's diffraction limited optics. And so here we just run a few experiments. Here, a few typical micrographs. This is just for 2D. Here we just set up, I mean, the experiment, so it's not real data. We know the point spread function, the noise. And, I mean, here it's just, okay, this image actually, L2 works pretty well. And I was saying, yeah, L1 almost always works better, but not always. There's still a few images that you can find where L2 works well. And usually I would say if there's lots of texture, actually, where L2 works well, but otherwise, like L1 would work better. But here's some real data. So this is like a bright field micrograph, so maximum intensity projection, so that's the raw data. And that's after deconvolution. And this is probably one of the applications where deconvolution really works pretty well, because we have a pretty good understanding of the model that depends on, on the characteristic of the microscope, and so that's the deconvolved image. We can also do that for X-ray tomography. So here are like line integrals, which gives you radon transform. You can also discretize your problem. So here you can run the algorithm, for example, on Shep and Logan. That's pretty much liked by compressed sensing people, or more realistic cut of a chest through the chest here. And I mean, for this image here, of course, like very sparse, like log prior works pretty is the best. And here, for this type of image, for example, like Gaussian works better. Now for those experiments, we just use L as the gradient, and we tuned all three parameters to get optimal signal-to-noise ratio. Now here's another application is on cryo-electron tomography. It's an old technique, but actually in recent years there has been a revival because of new detectors. And in fact, last year in Nature, it was discussed as the method of the year, so for structural biology. And so here's a reconstruction of a 3D virus, papilloma virus, using the usual Fourier type reconstruction. And it's reconstructed using like maybe 20,000 projective views. The difficulty is you don't know the orientation. And it's a direct algorithm. And they use a direct algorithm because they have so much data, they need to be fast. And now if you try to crank the resolution with this Fourier type reconstruction, it doesn't work. Now my student, Massi, here who now actually passed his PhD exam, now actually developed a fast algorithm that is able to do it with the L1 and the sparsity paradigm. And so there, I mean, we can actually improve the resolution. And now we are trying to do an international competition, trying to show that our algorithms, are better than the others. But, it's not so easy, but we're working on it. Okay. Now, summary, sparsity in infinite dimensions. So now if you work in the continuous domain, you have to forget about linear algebra. Now you're working in some function space. But now you're still getting measurements, and now this measurements is a mapping from this infinite dimensional space onto finite number of measurements. And then we have a signal model, and here it's a partial differential equation. And it's Ls equal W. So if you want to remember something from my talk, it's really easy, Ls equal W. Okay. And now what about splines? Actually, the W is the innovation. And actually, the splines are the signals that have the sparsity innovation. And actually, our new results show that. So if you define this generalized TV, so it's like, roughly speaking, is a weak version of the L1 norm of Ls. The solution of that problem will always be splines. Actually, it's not unique. There are many possible solutions. And in fact, it's the extremal points of the solution set that are splines. So it's a quite strong theorem. In fact, we can even consider any convex functional, and it's still splines. It's not just this L2 data term. Any data term is still splines. And any modality is still spline, any linear inverse problem. So it is remarkably general. And now, so that's if you're a deterministic guy, or looking in infinite dimension. Now, if you prefer statistics, we have the sparse stochastic framework, and actually it's really compatible. It's almost the same algorithms. And so we have this distinction between Gaussian and sparse. So Gaussian goes with L2, sparse goes more with L1 or L0. And a map will enforce sparsity through non-quadratic regularization. Okay, so here I have to acknowledge many, many people involved, all the people in my lab, collaborators, ERC, Grant, I have to be very thankful. And okay, so here maybe something to remember, take-home message, you like art? So if you're a Gaussian person, you may prefer this type of painting, it's Pollock. And now if you go to sparse, you prefer this kind of painting, Mondrian. And by the way, I have also an acoustic counterpart of that. I will just do it like that. If you are a Gaussian guy, you like, and if you are a sparse guy, you like chimes, okay, which is the counterpart of sparse. I mean, if you go on our websites, there's some audio demos. Now, if you are a Gaussian guy, you like Fourier analysis. If you're a sparse person, you like wavelet analysis. Oops, yeah, you know, Swiss timing. Okay, now you need to put the right people there. So if you're a Gaussian guy, you like Norbert Wiener. And if you're a sparse guy, you should like Paul Levy. Maybe you don't know him, but go and study. It's, you know, it's also very, it's at the same time as Wiener. It's 1930, 1940. So, you know, that's sometimes the references I use in my work, they go back to the 40s, okay? I mean, those guys were really very, very good mathematicians. And, of course, if you're a guy like me, you sit in the middle, like splines. Schoenberg. You know, Schoenberg, he invented splines about the same time as Shannon invented this sampling theorem. And actually, Schoenberg was a pure mathematician who was forced to do applied work during the war. And that's when he did his splines. Anyway, so that's the story. And here are some references. So if you want to know more about sparse stochastic processes, so there's a book. Actually, it's even at the Cambridge University Press. No, I was asked to do some advertising. But you can also go here. It's not a Russian website. Okay, otherwise, this L1 optimality of splines is very, very recent. We just posted it on archive, so you're welcome to download. It's a little mathematical, but I mean, to me, this is really amazing because it sort of puts everything together. And otherwise, here are some papers on application. There are many more if you go on our website. Okay, thank you very much.
Thank you. Do we have some questions from the audience?
Which I haven't heard before about solving that sparse recovery problem. One is ADMM, that's effective, and the second one is a Fourier-based method, which you name the nature name as the method of the year. So how do they fit into the traditional way of thinking of the classes of the solutions. One is what I remember based on greedy method, and the second one is based upon lasso method, and the third one, I think recently one also, we see some Bayesian method and also neural net method. As a matter of fact, on Friday there will be a method, some paper posted there. So I would like to see the connection between the method and some method.
Now the guys in nature method, you know, like going to the method of the year, actually they were still talking about old style reconstruction. So the Fourier method goes in the filtered back projection, like my second slide. And actually the reason those guys, they were not using iterative algorithm, it's because the data is so huge. It would take them, especially also like in those days, I mean this thing, the methods were designed maybe 30 years ago. The iterative algorithm, like they had like art or so, they're so slow that it would take them, you know, many years to reconstruct that iteratively. Now with ADMM and FISTA, this type of method that people actually in compressed sensing have developed, now we are at the point where actually our new iterative algorithm, they're about like 30 times more expensive than the Fourier. So now we're really at the time where we can run those algorithms. Now, how does it fit all this? Actually, you know, I'm more trying to unify here. And my main point is, you know, however you look at the problem, either you are, let's say, total variation L1 guy. Actually, what I'm telling you, if you do it in the continuous domain, which people don't do it, but you find a spline. Actually, people know with TV that it produces piecewise constant. That's the reason why compressed sensing, people like Shep and Logan, okay, because it's piecewise constant. So the theorem here is more like an existence theorem. It explains what goes on. And actually, what's amazing is if you go in infinite dimension, you can actually do the math. Okay, it doesn't tell you how you solve it exactly, but at least it explains to you the nature of the solution. And now, for example, if you were not using first derivative, if you were using second derivative, the guy would be piecewise linear. If you use fourth derivative, you know, piecewise cubic, etc. So it really tells you how this regularization affects the solution. So now, okay. So now the thing with the Bayesian, now so far I've just talked to you about maximum a posteriori, and that's probably not the best if you're non-Gaussian. And so we are now working on more like minimum mean square error, you know, with message passing, and actually there's lots of work to do there to go beyond maximum a posteriori. But what's nice here, we have probability models. And so then, I mean, there's lots of advanced signal processing to do here. It's just more the framework, and it's more like people like you to design the algorithms.
We have one more question.
Hello, thank you very much for the talk. I'm just very curious about the application side of the algorithm. So for example, have you, maybe you could talk us a bit more about the application of this algorithm in other areas, especially for electrophysiology signal like EEG. For example, in brain area that what we're trying to do is we measure the signal from the scalp because we don't insert needles inside the brain. But what we are trying to do is from the measured signal on the scalp and then try to infer where the source is inside the brain, but it's a yield impulse problem. So I wonder if you have actually applied this or think about
okay. So
and what's the limitation of that in that sense?
Okay, so very, very good point. So I'm more imaging person. So I have applied it, you know, to refractive index tomography, diffraction tomography, MRI, CT, deconvolution, structured illumination, at least 8 or 9 modalities. Almost anything where you do reconstruction, you can apply it. Now, for the thing of the physiological signals and this thing of you know, EEG, etc. So it's not so much my type of work, but I can tell you essentially, very pragmatically, look for the word sparsity. And so I have colleagues who have applied, for example, those generalized total variation to try to, for example, try to find the onset of activation in the brain. And also this spiking of neurons and all that. So that's very, very relevant. Let's say, you know, you could just say this sparse stochastic processes, it is the sort of statistical counterpart that would work with sparsity. Because if you do linear algorithm, it goes with Gaussian. There's almost like a isomorphism. I mean, you could like rewrite all your algorithms using Gaussian statistics. Now, if you are more a sparsity person, I would say those type of models now give you statistical models that you can still try to identify. Actually, that we haven't done. There's lots of work to correctly identify the models and then just you use statistics actually to solve those problems where sparsity has been shown to work.
All right,
So there's lots of work to do.
That's great, thank you.
Okay, so we will wrap up the session now. I'm sure Michael will be around afterwards if you have questions for him. I have a small gift from the organizing committee to show our appreciation for the talk. So thank you very much.